in the further development of these methods. The reason is that it really, for the first time, allowed you to look at the results of a complicated pulse scheme in a straightforward manner. And this is why this method has proved to be a turning point in development of two-dimensional NMR spectroscopy, further development of two-dimensional NMR spectroscopy. To be precise, to be quite honest, one should really have studied this before we started the COSY experiment, and we did use it without having told what the method is, because it's almost indispensable. But I have put it in the later part of the lectures because I didn't want to drive people away already right in the beginning with too much mathematics. And so, although it was a little inconvenient to use it even without having introduced it. Okay. The method was outlined. It was actually somewhat used even before that. And in fact, the vector notation is somewhat using the formalism all the time. And it was but formally put forward and, in 1983 in this paper, In Progress NMR Spectroscopy. And it is extremely useful for, as I said, for studying coherent correlation, correlation by coherent coupling. Well, before we jump into the method, let's see what are the ways we could talk about coherence transfer before this method came up. And the first one was, of course, the classical vector model, which is strictly speaking applicable to only a single spin half system without couplings. And so it really cannot describe a transfer of coherence from one spin to another. And but people did invent some ways of talking about it, and one could use it for very simple cases. There was another method which was introduced, which is called semi-classical vector model method, which basically used single transition operators. And then there was an algebra given out for the commutation rules of those single transition operators. And it was very useful algebra, except that basically the single transition operators were useful for describing selective experiments. And as soon as one wanted to describe non-selective experiments using the single transition operators, it became rather complex and not much useful. Also, there was some problem in describing transfer from one transition to other if they were sharing a common energy level. We will not be discussing this at all, but just as a review, tell you what was available. Of course, the method for the ultimate method is the density matrix approach, which is the correct one, and it takes care of coherence and coherence transfer and strong coupling, as well as relaxation if put in properly. And in the eigenbase of the Hamiltonian, the various elements of the density matrix have physical meaning, meaning by that the diagonal elements represent populations and the off-diagonal elements represent coherences. The problem with the density matrix method is that if you do an experiment and do a calculation for that experiment, then what you see, the result is after the final trace is taken. Intermediate steps don't really tell you much. You don't have them unless you calculate again trace at the intermediate step. So the problem with the density matrix method is that it doesn't give you a physical picture all the time as to what is happening, and only at the end you see that. And of course, it becomes quite tedious if you have more than a few coupled spins. Okay, and this was the basic development with the product operator method. Though in principle the product operator method is not very different from the density matrix method. It is using density matrix. What you do is you expand density matrix into certain basis of product operators, and you are really looking at the time evolution of the density matrix, but you talk about it in terms of the evolution of these operators. And so basically you are still looking at density matrix. The most powerful point of the product operator method is that you don't take traces. You already pre-calculate what the result of a particular operator will look like after you take a trace with the observable. Okay, so you fix your observable, that is, you're going to observe with an operator called I minus. Okay, you're going to take a trace of all the things with the I minus or I plus, whatever you decide. Okay, and then you predetermine, okay, if I take a trace with the I minus with Ix, what will I get? If I take the trace with the Ix with Iy, what will I get? If I take the trace of I minus with Ix, Ix of spin 1 and Iz of spin 2, what will I get? And all this information you store with you. And then you just calculate how these product of operators evolve at the end, and so you know the answer without taking a trace. Not only that, intermediate steps also, as you see these operators, you know what the result would be at intermediate steps. And that is the power of this method. And it was extremely useful in particular for two-dimensional NMR spectroscopy, where you apply several pulses, and or it will be useful anywhere where you apply several pulses. And so you have to have a feeling as to what is going on at intermediate steps. And the product operator formalism basically does the following. It expresses the density matrix in terms of product of operators which form a basis set. What basis set we have, we will come to a little later, but let us see what the basis set that have been used earlier in expressing density operators. There is a basis set which is using irreducible tensor operators. Several people have worked on this direction, and these are operators like Iz, I plus, I minus. And these form a nice orthonormal basis. They have very good transformation properties and therefore are extremely easy to handle whenever you're doing transformations. But the result that you get is not so clean. And you again get a jumble of operators from which you have to sort out what the result is going to be. They have nice transformation properties, but the result requires again calculation of traces. Then second is the single transition operator, which I already mentioned before, and this is again a basis in which the density matrix was expanded, and I have already talked about that. The basis that we have chosen, or these authors have chosen for expanding the density operator, can be written down in a formal way with this formula. But I find it very inconvenient to look at this formula. I want to straight away go into the basis set that you can derive out of this formula. I don't want to say much except that K represents the various spins that are coupled to each other. The nu represents the X, Y, and Z components. The A is a number which will be either 1 or 0, which means whether that operator comes in or not. And Q is the order which goes from 0 to n. And Q is of course important because that determines the order of the coherence. Okay, the number of operators here determine the order of coherence. Okay. This is also only for spin half. There will be another set which will be for spin not equal to half or 1 or 2. Okay, that's down below. All right, let's see what the basis set is, for example, for a single spin half. For a single spin half, n is equal to 1, and q can take values 0 and 1. So we have 4 operators, unity operator, I1x, I1y, and I1z. The 1 is not a necessary subscript because we are talking about a single spin here. So basically, unit operator, Ix, Iy, Iz. These are the basis in which you want to expand your density operator. That's sort of trivial. We already have this feeling as to that's what we do in a single spin case. Okay, some people might have already noticed something interesting here, but we'll come to that. Okay, for the 2 spin it's interesting. What are the basis set? For q equal to 0, we have a unit operator. For q equal to 1, we have, that means single operators, I1x, I1y, I1z, I2x, I2y, I2z. That's 2 spins coupled to each other, spin halves. And so we have these 6 elements. And then we have the basis operators as I1x, I2x, I1x, I2y, I1x, I2z. I1y, I2x, I1y, I2y, I1y, I2z, I1z, I2x, I1z, I2y. Very simple products. These are the products of the operators. Okay. And we have these 16 operators, which is the dimension of the basis set required for this purpose. Please notice a misprint in the next, this trace BRBS, instead of BR is written there. It's BRBS. Okay. Now, there is one, the product operators are orthogonal but not normalized. So it's not very good, but the reason is that's because that you have the convenience of the final result looks simple. Otherwise, you will have to multiply by certain normalization factors, which will again have to be remembered every time you calculate the, you have the operator. And so this bad part of it, people have accepted in order to keep it for the sake of simplicity. So when they say they are orthogonal, essentially meaning by the trace of operator BR with BS, that means R and S are 2 different operators from the basis set, is given by 2 to the power n minus 1 delta RS and not only delta RS. That is what that means, that they are not normalized. Right? Example is that if we take a trace of I1x with I1y, we get a 0. But if we take a trace of I1x, we don't get 1, we get a half. Okay. So this is the not normalized, but orthogonal. So I think the orthogonality is more important. Normalization is something that one can correct for if necessary in a transformation. And the most important part of these operators is the interpretation of operators. Okay, and then we do want to do the interpretation. And we are going to apply them for a very specific purpose here. The purpose is to describe the high resolution NMR spectrum of spin half spins coupled by J coupling, weakly coupled and not strongly coupled. Several people have attempted to give product operator algebra for strongly coupled spins. There are 2 or at least 2 formalisms that I am aware of, but the most important point of the product operator algebra is really this simplicity. And the simplicity is basically lost as you try to build up the algebra for strongly coupled, and then people just go back to the computer. So, therefore, and of course, weak coupling, we will, and also one should have a resolved multiplets, otherwise the result is not useful. And we also will make the assumption of ideal pulses. Okay, now we come to the interpretation. And let us start with the simplest of them. Okay, 2 coupled spins, K and L, each spin half. The operator IKZ represents longitudinal magnetization of spin K. And if that means in terms of populations, that will represent a population distribution which is of this type. It is not an equilibrium population distribution. It is different from equilibrium. The equilibrium is actually this one, where it's I1z plus I2z. And the population distribution is from a Boltzmann distribution, and when you make the approximation of high temperature, it's basically you have the excess population in this level, and as much excess population here, as much depleted in this level, because they are separated by 1 omega from here to here, another lambda frequency from here to here. Okay, so this is the equilibrium population distribution. I1z plus I2z represents equilibrium. But only I1z is a case where the essentially it is saying that this transition will be observed and this transition will not be observed. So the spin 1 transitions will be observed, spin 2 transitions will not be observed. I1z is a population distribution which is different from equilibrium. IKX represents a coherence or X magnetization of a spin K. And it is in phase, meaning by that if you are going to think about a coupled spin system, a 2-spin coupled spin system, because we are talking about the case of 2 spins here, then both the transitions will have the same sign. If I will take a trace with I minus or I plus, I will get the result which will look like this. That is, both the transitions are up, and IKX, basically wherever you see IKX represents 2 lines of K spin both up. Okay. IKY also represents in phase, that means both the lines are having the same sign, but they are dispersive. Okay. Represents coherence of the spin K. And that means these coherences are complex, have a real part and an imaginary part. So far it was simple, or something that we know. Then something that we have already used previously, but we had not really introduced it formally, is in operator IKXILZ, which says it's a X magnetization of spin K, which is antiphase with respect to spin L. And if K and L are the coupled spins, then the 2 lines of the K spin will have this property. And that is the thing that is represented by this operator. If you take a trace of this operator and calculate the result, this is going to be the result. In terms of coherence, it says this is going up and this is coming down. Okay. Antiphase with respect to spin L. That is the language we are going to use. In fact, have used so far already. Then there is another one which is quite interesting, which says IKZ ILZ. IKZ ILZ. And that is a longitudinal 2-spin order. That's called longitudinal 2-spin order. And it is something that we are not normally encountering. And it's not easy to create also. It is a population distribution which is somewhat strange, and of course doesn't give you any net magnetization. Although you see, this one will give you plus, this one will give you minus, this one will give you plus, and this one will this one will give you plus, this one will give you minus, this one will give you plus, this one will give you minus. And so it's some kind of a rearrangement of these. But what it says is that the 2 spins K and L have a correlated order in the Z direction. 2-spin Z order, we call it. This is different from this one, I1Z plus I2Z. I1Z, I2Z they are not correlated order. Okay, they are independent. I1Z plus I2Z is quite normal. That's a normal equilibrium population distribution. I1Z, I2Z is a very different one, which says it's some kind of a longitudinal 2-spin order, we call it. Okay, it's a very useful concept. In fact, but we are going to use it very much in the lecture number 14, where we will discuss coherence transfer via longitudinal spin order. And this is the kind of spin order that we are talking about at that point. Okay, then we have further terms which are very interesting and have no analog in vector diagram for these, strictly speaking. Then some people do invent vectors for them, and I get confused all the time. Okay, and this is the IKX ILX, which is basically 2-spin coherence. 2-spin coherence, and contains, this is the 2-spin coherence of K and L, this is the 2-spin coherence XY and YY, XX, XY and YL. All are 2-spin coherences and contain double quantum and zero quantum coherences. The mixtures of those. And these terms are not directly detectable. Similarly, these are not directly detectable. You have to convert them into detectable magnetization. On the other hand, these terms are directly detectable. Okay, and these are not detectable. These are not directly detectable. You have to convert them into detectable terms. But you can calculate what will be the pure double quantum coherence out of those several terms. And what you have to do is take the kx Lx minus ky Ly, it gives you a pure double quantum coherence. Okay, which can also be represented, this is equal to Ik plus Il plus, which is not a basis operator. We are not, this is not a basis operator, so we don't think about it very much, except that it's easier to see why it's called a two-spin order, because both k and L spin go up simultaneously, or both k and L spin come down simultaneously. As this is easy to see from this operator, and that's why it is called a two-spin, double quantum coherence. And so this is a pure double quantum coherence. And in terms of density matrix, it means this element and this element are populated by this operator.
That means if you assume that this combination is the density matrix at that point, is that right?
Yeah.
Calculate that density matrix.
Yes.